discuss about the device characteristics of light emitting diodes. Before I proceed with the device characteristics, let us recall in the last class we had looked at the device structure, and broadly there were two classifications: surface emitting LED and edge emitting LED. This is the abbreviation ELED, edge emitting LED and surface emitting LED. The structure in 3D looks like this. So, the dotted region here is the layer, is the active region. Everywhere the dotted region is the active region, and the shaded region is the metallic electrode. In surface emitting LED, since the light, so this is what is shown here is the cross section, a segment. If you take a segment in the along this line, so this is what you see, the cross section. Similarly, if you take a segment, longitudinal segment along this line, then this is what you see. So, what is shown here is the longitudinal section of this, and here this is the section. So, that is why you see this here. It is actually a circular electrode there, and an annular electrode at the top, and we have already discussed that the annular region is because the emitted light has to come out. So, the generated light has to come out here. So, that is why we have usually there is a window, dielectric window there, and an annular electrode. So, I had taken for example gallium arsenide substrate and so on. So, N gallium arsenide substrate, and then you have L gas layer, the cladding layers which are aluminum gallium arsenide in this particular case, and an active layer in between, which could be a different composition, aluminum gallium arsenide or gallium arsenide. So, that is the active layer. So, the structures look almost similar, and there is a window here and the light comes upwards here. There was a question that the light which goes below, that is into the substrate, so this is usually lost, it is a waste. In both the cases, light that comes down here is a waste. In this case, of course, light which is going here is also lost, because we are primarily collecting light from the edges. That is why it is edge emitting LED, making use of the optical confinement property of a double hetero structure, light which is coming out here in the form of a cone from the edges. In this case, it is coming, the edges, the light which is coming here at the edges are lost, that is not made use of. But in both cases, the light which is going down into the substrate is lost. There were some efforts to, there are some designs where one can make use of this. For example, there are designs in which you have a Bragg reflecting stack here in the cladding, a Bragg reflecting stack. So, this is called a Bragg stack. So, let me zoom in and show you what is this Bragg stack. So, the Bragg stack is basically a interference filter, high reflection, low reflection, periodic, high index, low index structure. So, N high, N low, N high, N low. So, it is a periodic medium, N low and so on, N high. And you know that such a structure, if chosen properly, that is if you choose the thickness of this D is equal to lambda divided by 4N, then such a structure acts as a high reflecting. So, if the incident light which is here is reflected back resonantly, this is the interference filters. So, the light which is incident gets reflected back. So, if you choose this as lambda by 4 layers, the thickness of lambda by 4, alternatively high index, low index, high index, low index, a particular wavelength that satisfies this, for example, lambda 0 divided by 4N will get lambda 0 will predominantly be reflected back. So, if this radiation is at a particular wavelength, then all of them can be reflected back. You can make these high low layers again by a combination of gallium arsenide, aluminum gallium arsenide. It is a Bragg stack comprising of gallium arsenide, aluminum gallium arsenide. because the refractive indices are different. Aluminum gallium arsenide has a higher refractive index. We will discuss more about this later when we discuss VCSELs, that is vertical cavity surface emitting lasers, which are designed on the basis of Bragg stacks. So, we will discuss about this later, but for the time being I wanted to mention that there are designs where the light which is going into the substrate can also be reflected back, so that overall efficiency is higher. This is for a particular wavelength. You can make a range of wavelengths, because we know that light emitted from LED is not monochromatic at one wavelength. There is a range of wavelengths which is emitted, and you can make this stack reflecting for a range of wavelengths by chirping the period, by choosing D of it. Right now, if you take a periodic structure, the refractive index variation would look like this. So, this is the what I have plotted is n versus x, the depth direction. So, n, this is higher index, this is lower index, n L, lower index, higher index, lower index. So, but it is a periodic refractive index variation. But you can change the period, which is called a chirped grating, a chirped grating. So, we will discuss about this later, chirped grating, which simply means the period is changing with x, and you can design chirped gratings which reflect over a wide band. If you see those of you who are familiar with the Bragg gratings, if you see a perfectly periodic reflectivity of a perfectly, so what I am plotting is R here versus wavelength lambda, then the reflection curve looks like this for a perfectly periodic square wave. But if you chirp it, then this band can get widened, and you can, it is possible to design wide band reflectors using chirped grating. So, some designs also include this, but one has to see whether one would like to go for this or not, depends on the application. If the application demands, then only one would go, otherwise the cost of the device will go up. Any additional layers, any additional fabrication process will add to the cost of the device. Therefore, only in such cases where you really need very high efficiencies, one goes for such designs. One last point which I wanted to mention here was that, as you can see, we have discussed this, that light that is coming out comes only up to a cone, because beyond that it undergoes total internal reflection. Light within this cone will only come out, rest of it will get totally internally reflected. There is a technique which is called texturizing. This was discovered much later, texturizing the surface, texturizing surface. In surface emitting LEDs, the efficiency can be enhanced by texturizing the surface. What is this texturizing? So, this is basically making the surface uneven. In simple terms, it is nothing but making the surface uneven, texturizing, and that increases the efficiency. So, you have, let me show this. So, here is a plane surface, then you have light which is coming up to this, goes grazing, which means any angle which is higher than that will get totally internally reflected, and an angle lower than this will come out. That is considering a perfectly plane surface. Suppose I damage the surface, texture, I mean deliberately I make the surface, just I am exaggerating. So, let us say I have a surface which is like this. In this case, this is not true, because a ray of light in this particular case, see here, it is hitting this interface not at critical angle, because the surface itself is like this, and therefore, this can simply pass through. because of the nature of the surface, because of the corrugations in the surface, most of the light will get scattered and pass through. So, you could have light passing very easily through such a substrate. For example, this particular one may get reflected here, it may undergo total internal reflection here, but from here it will come out. So, by texturizing the surface, how this is done? This is done by using sandblast of glass spheres, using a technique which was using glass spheres approximately diameter 1 micrometer, blasting the semiconductor surface that causes texturization. It is a sphere, therefore, it is not spoiling the surface, but it is texturizing the surface. So, using this it has been shown that the emission efficiency, extraction efficiency increases. The reflection losses can be reduced by using such structures. In fact, now currently there is some research going on in using photonic crystal structures, periodic photonic crystal structures on the surface to enhance the extraction efficiency. All right. So, I hope the structures are now clear: edge emitting LED and surface emitting LED. One other point which I wanted to mention is, here we know why the dimension of the electrode is reduced, because we wanted that the carriers flow like this, so that the recombination takes place in the central region and light can come out. If the electrode was fully up to this, carriers would have also flown here, and that is why we are using such an electrode. What about here? Why this was reduced? You see, this layer here is a dielectric layer, it is a blocking layer, SiO2, and metal is only here. So, the carriers flow like this. It is a strip. The metal is in contact with the semiconductor. This is semiconductor. So, this is P-Al gas, let us say, that layer, and the next one is N-L gas, and in between is the active region. The metallic strip is like a strip. It is not the whole, it is not a layer which is in contact with the entire layer of semiconductor. It is only here. Why is this? What is the reason? If carriers go from here, you can see the light is generated only in this region, because recombination takes place only here. So that when light comes out here, you get a cone of light which is coming, or a beam of light. Otherwise, light would be generated over the entire sheet. So, you would get a sheet of light. One reason, but that is not the primary reason. What is the reason? Why this has been, the width of the electrode has been reduced? Recall that we had an expression, recombination is equal to delta n into tau, and we had seen that this multiplied by volume is equal to the charge which is flowing, I by E. If I is the current that is flowing, then by I by E is the number of carriers which is entering the semiconductor, which is equal to rate of recombination multiplied by the volume of the region where it is recombining. V is the volume of the region where recombination takes place. So, this expression we have. So, therefore, please see this. So, this therefore, if I multiply by V here, I should multiply by V here also to the right. R is equal to delta n by tau. V into R is equal to delta n by tau into V, which is also equal to I by E. I could written I by E here. So, we have delta n is equal to I by E into tau divided by V. Now, I am taking the last two here, and delta n is equal to I by E by V into tau. What is V? V is the volume of the active region where recombination is taking place. So, this volume, this V is equal to length into width into thickness. What is L? Let me show here. L is the length of this region. Please see, current is flowing here. There is a current I which is flowing through the device. I can show with respect to this or with respect to this. The current is flowing there, I. This is the length of the device. What is the width of the device? If I reduce the electrode, then effective width is only this. This is the width of the device. So, this is W, the width of the device. This is the width of the device, because the V here stands for the volume where recombination is taking place. Therefore, recombination is taking place only here. So, length of the region multiplied by width, and what is D? D is the thickness of this region, the active region. So, L, so D is thickness of the active region, that is thickness of active region, thickness of the active region. V, W is the width of the region of the recombination region, which is approximately equal to the width of the electrode which is in contact here, the width of the electrode which is in contact approximately equal to. And L is of course the length of the region. Now, when we talked about double heterostructure, I have already discussed the importance of D. By taking a small d of 0.1 micrometer or 0.2 micrometer, you are able to confine the carriers to a small region, and therefore, you could increase the density the carrier density delta n by reducing d. If that is the case, so let me write this again, expression here, delta n is equal to I by E into tau divided by L into W into D. For a given current I, delta n can be large if any of these three or all these three could be as small as possible. So, D we have reduced, thickness of the active region that is reduced, therefore, delta n increases for the same current in comparison to homojunction LEDs. W is the width of this here, and by reducing the transverse dimension of the electrode, we have effectively reduced W, and therefore, delta n can become larger. We could of course reduce L also. If we reduce L, the volume where light is generated becomes very small, and therefore, you have to strike a balance. In general, you could reduce all the three to get a large delta n for the same current, but D and W can be reduced without losing much, whereas if you reduce L, the entire volume reduces. W reducing will also help us to get a beam from this LED, otherwise you will get a strip over which emission takes place. Normally in applications you would like to have a beam, and therefore, W is reduced. This W is typically 5 to 10 micrometer. So, W is typically 5 to 10 micrometer, and D I have already discussed is about 0.1 to 0.2 micrometer in a double heterostructure. And in an edge emitting LED, L is typically, so L here is typically 100 to 300 micrometer. So, some idea about the real numbers of dimension of the devices. So, these two have been reduced. Why are we interested in a large delta n? A large delta n because the Fermi level EF moves up if delta n becomes large. You recall the expression for Fermi level, EF is equal to EC plus KT into ln n divided by NC plus 1 over square root of 8 n divided by NC. And what is this n? N is n0 plus delta n. Larger the delta n, larger will be this, and therefore EFC. So, EF when in quasi equilibrium, this is EFC, and EFC, the separation between EFC and EFV will increase if delta n becomes large. It depends on delta n, not the current, and therefore, for a given current, even by passing a small current, you can achieve a large value of delta n, so that the separation between the Fermi levels can be large. And as we know that separation between Fermi levels, why do we want larger separation between Fermi levels? Because the probability of emission would go up, and we know that the rate of spontaneous emission here is proportional to, it depends on if you have, so it depends on some number RSP at 0, that is thermal equilibrium, multiplied by, so this 0 is standing for thermal equilibrium, multiplied by e to the power EFC minus EFV by KT. For thermal equilibrium, EFC equal to EFV, so this term is e to the power of 0, which is 1, but in quasi equilibrium, the rate of spontaneous emission gets multiplied by this factor. This factor will be large if the separation is large. The separation is large if delta n is large. Delta n is large if dimensions are small for a given current. So, this is the logic why the strip width has been reduced. So, we in a given structure by now, we know what is the need for having such a structure, such layers, such combinations. Why do we need this? We now completely understand this structure, why such a structure is used in realizing LEDs, light emitting sources. We now proceed to the characteristics of light emitting devices. Just before I proceed, one last small point here, that is, I have written like this. So, this, if you recall, L into W, what is L into W? Length into width gives you the area of the strip. L into W gives you, recall the active region. So, before erasing I should have checked. So, this is now front view, okay, cross section. So, here is the strip, metallic strip, and under this so many layers are there. All right, let me draw the layers again very quickly. Okay. So, the carriers are flowing like this, and this is the active region here. This width is W and L is the length. So, you have a strip of area L into W is the area through which current is flowing. Current is going from top. Please see this. This is I. Current is flowing through an area L into W. L into W is the strip width, strip area of the strip. L into W is the area of the active region through which current is flowing. Therefore, I divided by L into W is what? The current density J. Therefore, delta n is equal to J into tau divided by E into D. This is an expression we would need later. Delta n is equal to J tau by E into D. D is the thickness of the double hetero structure, active layer, tau is the excess carrier recombination time, J is the current density, because when we go to semiconductor lasers you will see that normally it is discussed in terms of J, the current density. That expression has come right from here. So, we will use directly this expression later when we get it. I would not again derive and show you from where we have got it. So, this is from where we get this expression delta n is equal to j tau divided by E into D. So, device characteristics. There are some important device characteristics which we need to discuss about. One, the IP and IV characteristics. It is a diode. This IP is current versus power. This is sometimes also called as LI characteristics. LI characteristics, light current characteristics. Some literature, some books may write it as light current characteristics. This is I versus current versus optical power, LI characteristic. Wavelength spectrum. Or sometimes this is called as spectral distribution. Emission pattern. So, when any user wants to use an LED, he has to know all these emission pattern. It is also called angular distribution, angular spectrum, emission pattern. It is also called as angular spectrum, sometimes radiation pattern or radiation pattern. Normally with antenna people use radiation pattern. And fourth, modulation bandwidth. We will discuss these important characteristics one by one. Let me take up the first one, and IP. So, let me erase this. We will discuss the first one and then come to one by one all the four characteristics. Now, this is completely from the user point of view. We have seen the physics of the device, the design and the structure of the device. So, IP characteristics. First, IV characteristics. IV is LED is a light emitting diode. It is a forward biased diode, and therefore, the IV characteristics, if you want to measure this IV character, so V versus I. Of course, you can also measure the reverse characteristics. So, it is the same, it is a diode, so it is the same diode characteristic. If you measure the IV characteristics, you will see the same diode characteristics. So, typically here is a cell and there is a series resistance Rs, and here is the diode, the LED. You can vary the voltage and you can measure the current. So, I, MA and Rs, a series resistance. simple IV characteristics, and LED gives out light. The LED. So, vary the voltage and you can see that the current increases if the same the forward diode characteristic and the backward reverse diode characteristics. Important point when in practice is to know that you have to put a resistance Rs. Every device is characterized by IF max, the maximum forward current through the diode. If you see the data sheet of a LED, there will be IF max, the maximum current. So, if V0 or V max is the maximum voltage here, then you have to choose IF max equal to Rs. The series resistance, before you start measuring this experiment, before you do this experiment, first calculate if you are using a supply with maximum voltage V max, and if IF max is the device forward current, maximum forward current, then use the resistance Rs in series, so that by mistake you do not exceed the current, so that the diode does not get damaged. So, the series resistance is to protect the LED. This is the IV characteristics, one can measure it very easily, and I am sure some of you are doing this experiment to measure the IV characteristics. I come to the next characteristic, IP or LI characteristics, light current characteristics of a diode. This is very important. So, LI characteristics, LI or IP, okay, LI. So, what do we expect? So, current I through the diode versus optical power. So, P optical. What do we expect? We expect a linear curve, because we have already derived the expression that P out is equal to eta external quantum efficiency into I by E into h nu. Therefore, P is proportional to P out is proportional to I. So, we expect a linear characteristic here. So, do we get a linear characteristics? Many of you have measured this. This is not wrong. So, we should get a linear characteristics. Yes, you do get a linear characteristic. So, if you take a surface emitting LED, you get a linear characteristic up to some region. So, this is SLED. If you take a edge emitting LED, it will also show almost similar characteristics. Edge emitting LED has a, for the same current in general, ELED gives a little bit less power, because only the light which is trapped on the strip is what is coming out, whereas in surface LED it is the radiation is emitted over a wider cone, and therefore, the power is slightly higher. But the characteristics look the same. It is output is proportional to input, optical power, P optical is. So, why does it saturate here? So, what are the reasons for saturation? This is fine, the initial portion. So, typical numbers if I were to put, so this may be, so 20, 40, 60, 80, 100. So, around 100 milliampere, this is I milliampere, and this could be say 0.5, 0.5, 1, 1.5. What is the unit? Milliwatt. So, typically 1 milliwatt optical power around 60, 50, 80 milliamperes of current, maybe 100 milliamp of current. So, typically this is the kind of numbers that you would get, or maybe hundreds of microwatt. For tens of milliampere, generally you will get about this. So, after some time you can see that it saturates. So, what is the reason for this saturation? So, let us focus on the saturated region. So, this is going straight and then it starts saturating and even starts coming down as current increases. So, this is I versus P. There are several reasons for this. The first one is Joule heating. Joule heating. It is a diode. The diode has an internal resistance. Current is flowing through the resistance. So, there is I squared R heat. So, Joule heating is because of I square R. So, I square R. This R is the diode resistance. So, there is heating of the diode. In fact, if you touch the diode, you can feel that the diode is getting hotter as the current increases. So, I square R, Joule heating. So, why should the heating bring it down? Because as the device starts getting heated, eta I, the internal quantum efficiency, goes down. This eta external contains eta extraction multiplied by eta I. So, this product is eta external. Eta extraction depends on the device structure. So, in the previous discussion we had how to maximize the extraction, that is what we had discussed. Now, eta I is a material parameter which tells you the fractional recombinations that lead to the emission of photons. The rest of it is by non-radiative transition, but as the device starts getting heated, there are the phonons in the lattice become very large and eta I starts going down. Most of the recombinations become non-radiative recombinations. So, eta I is in fact exponential dependence. So, if temperature goes up, if T goes up, eta I drops down almost exponentially. The internal quantum efficiency drops down because of the existence of large amount of lattice energy or phonon energy, which is responsible for non-radiative recombinations. And the fraction of non-radiative recombinations increase over radiative recombinations. Radiative recombinations are responsible for giving light. Non-radiative recombinations do not lead to generation of light, and therefore this is one of the first reasons. Let me write the reasons and then I will stop here and continue in the next class. The second reason is carrier leakage loss. And a third reason, which is applicable to SLEDs but not for ELEDs, is stimulated emission loss. Stimulated emission loss. I will discuss these points in the next class because we have to take a quiz. The quiz has been pending for quite some time. So, we will discuss this and see what do we mean by carrier leakage loss and stimulated emission loss. Today's quiz is 1 minute quiz. It is fill in the blanks. You should not take more than 1 minute. Okay. So, take out your answer sheet, write your name and keep ready. I will put the quiz and in 60 seconds you must close and give it. It's Just fill in the blanks, very easy. Don't let your eyes run this side or that side, just on your sheet. Okay, everyone ready? 1 minute, 60 seconds, no more. Quantum confined Stark effect refers to dash of the absorption edge of a semiconductor quantum well structure in the presence of dash dash dash. Fill in the blanks. Your time starts now. Fill in the blanks with appropriate words. The only unique words will fit in there. Quantum confined Stark effect refers to of the absorption edge of a semiconductor quantum well structure in the presence of. Okay, let me the answer is let me give you the answer also. So, what is the answer here? Nothing else will fit. Redshift. This redshift of the absorption edge of a semiconductor quantum well in the presence of applied electric field.